visual survey result to the IC5146. So yesterday, Kat has already introduced what is the visual survey. So in this talk, I will mainly emphasize one of our scientific goals, that is to resolve the magnetic field in the intermediate scale. So here this table roughly lists the resolution of different kind of observational instruments. So the Planck and optical near-infrared polarization have done many great works to resolve the magnetic field in larger scale, and also the interferometer can really resolve the magnetic field within the codes. But there is still a big gap between these two resolutions. So the advantage to use the single dish polarization is to really cover the scale between the large scale and the interferometer. So here we can try to answer the big question that what is the role of magnetic field from the filaments to formation of cores. So here I would like to draw your attention to this so-called half filament structure. That is describe the structure that consists of a dense hub connecting to several filaments. And this kind of object is important because they are often associated with young star clusters. So it is potential site that the material in the filaments that is converting to the mass of the young clusters. But this kind of object is still mystery because it can be seen in a variety of physical scale. So here shows two examples. The half filament system can be shown in the Ophicus complicates, which has a physical scale of more than 10 parsec. But it can also be seen in certain cells, and its physical scale is only within 0.5 parsec. So it's quite weird if all these kind of structures have similar origins. So here we can provide some information to really know what is going on with these kind of structures. So here is our target IC5146. So let's start from the very big scale. So here it shows our previous optical and infrared polarization, starlight polarization result overlaid on partial maps. So here we can see the system consists with a bright extrude region and connect to a long filament with the length of roughly 10 parsec. And our near-infrared and optical polarization shows the large scale magnetic field here is roughly uniform and perpendicular to the main filament structure. So here we want to zoom into the yellow box, which is the densest filament in this region, and we see this is you can see a similar structure that is 5 parsec length filament connecting to a dense hub, and here the filament is still roughly perpendicular to the magnetic field. So here the visual survey observe this region, observe the purple field with pole 2. So we can zoom into the regions within 1 parsec, and here we show the precision result from pole 2 and overlaid on the pole 2 total intensity map. So from the total intensity map, we can see there's a different filament structure different from the large scale. So we think a small scale filament that is extending from the northern to the southern and likely connecting to the central hubs. And the precision maps here shows roughly similar to the large scale, but you can see a big curve that is extending from the northern to southern, roughly along the filaments. So to compare the small scale magnetic field to the large scale magnetic field traced by near-infrared polarizations, here we plot the histogram of the polarization orientation, and here we show that actually the magnetic field traced by large scale and pole 2 have a quite similar average, but in fact the small scale polarization shows two components that is likely bending from the large scale magnetic field. So here you can see two components. So we just show where is these two components, and we see these two components are either from the top half or the bottom half of this system, and which suggests that this local magnetic field, the small magnetic field is likely inherited from a large magnetic field, but is possibly modified and directed by the contraction of the large-scale main filament. So in addition to the overall morphology of the magnetic field, we also want to investigate whether the magnetic field is important in regulating the fragmentation of clumps. So here we use the clumps identified in the descending global survey is the boundary shown here, and here we just try to calculate the clump orientation by the Gaussian fit. So here we can show that the orientation of the clump is roughly following the filaments from the northern part to the southern part, and here you can also find that the local magnetic field is roughly correlated with the orientation of clumps. So to emphasize these correlations, here we plot the orientation of clumps and also the average local magnetic fields. And here we find the magnetic field average near the peak and within the clumps. And here we find that these two plots show quite similar result, that orientation of clumps are either perpendicular to the either perpendicular or parallel to the magnetic field. And here I also want to emphasize that the alignment is between the local magnetic field and the clumps instead of large scale. So here the dashed line shows the mean large scale magnetic fields, and only the central hub, that is clump 47, that is really aligned to the magnetic field. That is really aligned to a large scale magnetic field, but all other clumps are only aligned to the local magnetic fields. So here I don't just want to then what we can learn from the results. So here we show the first observed feature. The magnetic field the small field magnetic field in this system is likely dragged along the per second scale main filament instead of toward the central hub. So it is unexpected feature, because if we assume all the materials will converge into the central hub, then we expect to see maybe an hourglass shaped magnetic field with its center at the central hub. But what we see is the magnetic fields are dragged by the large-scale magnetic filament. So it hints that perhaps during the time that the magnetic fields are modified by gravity, at the time the mass of the central hub is still very low compared to the main filament, or maybe at that time the dense hub are not even really formed. And the second observed feature is the clumps within how filament systems are aligned with the local and the pinch magnetic field instead of the large scale magnetic field. So it also favors the possibility that the hub filament structures are formed after the large scale magnetic fields are modified by the contraction of the main filament. So based on these features, we could suggest a possible scenario that is mainly based on the filament fragmentation simulations. So here we show the example that is from Survive at 2015. This shows the filament with filament can fragment, and the two massive fragments will appear at the 2 ends of the filament. So here we can show similar pattern that if the main filament show in a strong magnetic field, and when the filament becomes supercritical, it will contract and drag the large-scale magnetic field, and after it starts to fragment, the fragment can further collapse and form a hub filament is like what we observe. So to support this scenario, we just show the gas kinetics by the animation of the 13CO32 data. And here the animation is the channel map of 13CO data. And it shows that in large scale, the main filament is globally flowing to the two ends. So it shows that it's likely fragment. And in the observed hub filament structure, it's globally convergent to the filament, but it is more complicated because there are already some clumps formed even in the filaments. So it's more likely correctable collapsing of the collectible traps of the filament. So here is my summary. Thank you.
Thank you, Jia-Wei. I think we have time for a few questions. Okay, so let me ask one. I mean, have you tried looking at this and the SMA data to see if there is overlap in any of the regions?
I think maybe no, because this region is quite near, so it's center and it's very difficult to absolutely understand SMA.
Okay. Enrique?
Yeah, just concerning your last point there in your summary, numerical simulations, I think both by my group and by Evo Striker's group, suggest that actually the clumps and the filaments tend to form at the same time. But then because the clumps evolve on shorter timescales, there's a couple of papers from 2012 that show that spherical evolution is faster than filamentary evolution. Then the clumps become more massive and denser, and then the rest of the filament begins to fall into the clumps. But what's interesting is that initially, basically the collapse, like I described in my talk yesterday, goes into the filaments, and then just because there's perturbations, some regions grow faster, and those begin to form the hubs eventually. And then when the large-scale collapse finishes, then you get all of these filaments pointing towards the center. But so I think there's a number of simulations that you could compare your observations to.
Yes, but for this kind of observation, then it will be some difficulty to explain why the main fields are dragged toward the filament center instead of the hub center.
Well, I would say that if the filaments are just, the magnetic field is just being dragged by the flow, then that's exactly why you see it pointing in that direction. But we can talk.
Okay, so we have another question. One in the back.
So, IC5146 has that big H2 region in the tip. Did you see any effect of that H2 region in the morphology of the field and the curving of the field?
No, because the H2 region is very far from what we observe. The H2 region is the region in the left button, and what we observe is within the yellow box.
Do you have any observations closer to the H2 region?
No polar observation.
Okay.
Any other questions? If not, let's thank Jia-Wei again.